All right, everybody, welcome. So we've been talking about this concept of forces, right? This idea that interactions can be quantified through the use of forces. And the reason why we want to know about forces, again, is because when you know about forces, then you can understand how the behavior of motion, what the behavior of motion will be for an object. And this is a very powerful thing to be able to do. Now, throughout this discussion, we've only described a few types of interactions, right? We've described interactions such as the gravitational interaction. The gravitational interaction, which is described with the force of weight. So we've described this force of weight, and this force of weight, as you come in, there's graph paper on the back table, you're going to want to grab a piece. This force of weight represented by W equals mg, where m is the mass and g is the acceleration due to gravity. And it should make sense that it depends on the acceleration due to gravity because it's a gravitational interaction. Now, we described this force, and we have a way to mathematically calculate what the value of that force is. And there are a lot of forces in which we can come up with this equation, with this mathematical model to describe our forces. There are some other forces, though, such as the normal force. The normal force describes an interaction of support between a surface and an object resting on that surface. The normal interaction, the normal force from the support interaction, well, that normal force doesn't really have an equation that's associated with it. You kind of have to find it based off of context, because there's no mathematical one description for how to calculate the normal force. So we'll just leave it at normal force is equal to m. All right, we've seen other interactions. Tension is another one of these interactions. Tension is a force that, again, is dependent on the scenario that you're dealing with. If you had a jump start on the homework, then you'll notice that there's quite a few questions on tension, and there's no tension is equal to this constant equation. So again, context clues. So we go through and we start to describe these different forces. We're going to describe a couple more forces, a couple more common forces. Today we'll definitely get through the friction force, the force of friction. Will be the next force that we look at, and then we'll look at spring forces. Maybe we'll get through it today, maybe we won't. It kind of depends on how quickly we move through the sort of activity that we're going to work on today. So that's the goal. We're getting to this point where we understand how to take a value of force and predict an acceleration based off of it. So now we really want to build up and identify these different forces that might occur. So we start to build up a sort of toolbox of different forces. Looking at the friction force, we can have two different behaviors of friction. We can have what we call friction that is static friction. Static friction is the frictional force that keeps an object from moving. We take a look at this little device I have up here, and I can put a wooden block on this device, and as I raise it up, the block does not immediately fall. Why does the block not immediately fall? It's because there's a friction holding it in place. If you guys have a laptop, the laptop has grip pads on the bottom. That way there's a lot of friction between the laptop and the surface that's on it, and that gives it a frictional force that keeps it in place. So we have this force of friction that seeks to keep objects in place. This is what we call static friction. And oftentimes when we represent static friction, we'll represent it F with a subscript S. Force of static friction. We really have to pay attention to these subscripts. These subscripts tell us about the force that we are dealing with. So we have this static frictional force, okay? When we analyze a system, such as the block on the ramp here, right? We analyze the system, we can come up with one of these interaction diagrams. So we have the block on the ramp, and I want to take a look at this situation. So we have a ramp here with a block on it. I'll draw a picture, Analyzing a system, well, a good first step would be creating one of those interaction diagrams that we looked at however many seemingly years ago it feels like. It was only like 2 weeks though. We analyze a interaction diagram where we have the block, which is resting on the ramp. We have gravity interacting between the entire Earth and the block. And that seems to account for all of the interactions that are going to be important to the block. We think of the contact interactions as being the interactions that are caused by strictly what is physically in contact, and that's only the ramp and the block. And then we have non-contact interactions such as the gravitational interactions that occur at a distance. Anyway, we build up this interaction diagram by saying gravity acts on everything. Gravity acts on the ramp as well as the block. And then we have the ramp and the block interacting through a normal force. Yes? And then we have the ramp and the block interacting also through this force of friction. The friction interaction is between the surface the object is on and the object itself. Just like the normal force. The friction force and the normal force are interactions that happen between the same pairs of objects. We go on. We say, okay, I want to analyze the block. When I analyze the block here, I say that the 3 interactions that are occurring here are going to be, 1, the gravitational interaction of weight, and that always acts directly downwards. We have the normal interaction, and normal is the mathematical term that says perpendicular to the surface. Perpendicular to the surface. That means that the normal force will be perpendicular to the surface it's on. And then we ask about the direction of static friction. Static friction. Static friction, we can determine the direction one of 2 ways. One, we think about this idea of static friction. Static friction means the object's in place. If the object's in place, what do we know about the acceleration? 0. That's absolutely true. And if the acceleration is 0, what do I know about the net force? 0. The net force must be 0. So wherever the static friction is, it must be in a place that offsets these 2 other interactions. That zeroes out our 2 other interactions. And we think about what must that be. Imagine a tug of war, something pulling down, something pulling to the left. What does the third direction need to be? The third direction needs to be off in that, up and to the right direction. That's positive y direction if you want to think about it that way. And that would be your force of friction. Force of static friction specifically. F subscript s. And that's the new force that we're looking at. Okay, well, we take a look at this and we say, well, that's complicated. Is there another way perhaps we can figure out the direction? And the answer is yes. Because the force of friction will always be perpendicular to the normal force. It will always be perpendicular to the normal force. That means we don't think about it offsetting any other force. We think, okay, it must be perpendicular to the normal force. And if it's perpendicular to the normal force, that means that it's either going to be one of those 2 directions. You think about what must stop the motion, leaves only that direction for your force of static friction. Again, you get the same results. But that is to say that your forces of friction will always be perpendicular to your normal forces. Force of friction will always be perpendicular to your normal forces. Next week in lab, we're going to investigate the static friction case a little bit more. For now, I want to talk about a different case of friction. So in lab, we'll talk about this a little bit more. But I want to investigate another type of frictional force that'll be a little bit easier mathematically. And that is a case of not static friction, rather kinetic friction. Sometimes it's called dynamic friction. Kinetic friction or dynamic friction. This is a type of friction that, unlike static friction, is involved with the motion of objects. If an object is moving, sliding across a surface, we say that that sliding across a surface causes a static frictional force. We take this block, we take this block and we pull it across the surface and we listen carefully. You guys hear that grinding noise? Very slight, it's probably hard to hear. I push down on it. That sliding force, that sliding sound. The sliding sound is coming from the resistance that is caused by that frictional force of the sliding object going across the surface. So we have this frictional force that is caused on this sliding surface. Okay, let's analyze it in a little bit more detail. How do we do that? Well, first maybe we draw out a picture, right? We're going to draw out a picture of what we see here. We have a surface, and on the surface we have a block. The block has some mass m. With this block m, we are going to pull it horizontally with a rope. We pull it horizontally with a rope to the side. We ask, what are the interactions going on here? We build an interaction diagram. We build an interaction diagram where once again we have the block, we have the surface that the block is on, we have the entire Earth, and we have the rope. We have the four things causing interactions on this object. These four pairs of objects will cause multiple interactions on the block that we want to analyze. How do we represent multiple interactions on a block? Well, perhaps we take this and we build it into a free body diagram, taking into account only the interactions that are going to cross from the environment into the system. So those will be these four lines representing different interactions. Well, what are these interactions? What is the interaction that goes between the rope and the block? What would we call that? T, tension. Tension. We have a tension going between the rope and the block. Remember, ropes always cause tension type forces. Okay, what other interactions do we have? Well, between the entire Earth and the block, what interaction do we have? Gravity. We have gravitational interaction between the entire Earth and the block. And we put two interaction lines between the surface and the block. What might those two interaction lines represent? Not static friction, kinetic friction, because our block is moving, right? When I did my little pole here, we see it's moving. Moving indicates kinetic. So we might say it's a kinetic friction, F subscript K, for kinetic friction. Okay, we have one more line that I drew there. What's that last line? Normal force. Absolutely. Perfect. Perfect. Wonderful. So we have our interaction diagram. We know from our interaction diagram that our free body diagram will have four forces on it. Our four forces will be tension going to the right, weight going downwards, normal force. Normal is the mathematical term for perpendicular to a surface. Here, perpendicular to a surface is going to be directly upwards because our surface is horizontal. So we have a normal force going upwards, and then we asked about that friction force. Well, that friction force, when we talk about kinetic friction, friction forces will result in will resist motion. It will resist motion. That means it's going to be in the opposite direction of the motion. If we pull our block to the right, friction must be going to the left. That is absolutely right, because it is resisting the motion. And now we might see why I wanted to start with this over static friction. Because in this case, each of our four forces lie on the Cartesian directions, x and y. Before, when we had the inclined plane, well, we had two forces that were off axis, and that might create a little bit of a headache. We don't want to deal with that just quite yet. So we create this easier system to build. Sound good? All right. Newton's second law. Newton's second law says net force is mass times acceleration. When we use Newton's second law, we want to consider the net force in the x direction. The net force in the x direction here will be tension minus force of kinetic friction. And then we want to consider the vertical independently. And the vertical tells you normal minus weight. So we find our net forces. Seem okay? Any thoughts, any comments, any concerns? All right. Well, now we get to the point of asking question. How can we quantify this kinetic friction? What is this kinetic friction going to be dependent on? What is it going to be dependent on? And to analyze this, what we are going to do is perform a little bit of an experiment. And for our experiment, we are going to want to track, actually, I'm going to track off to the side here. We are going to track the weight of the block weight is a force. That force will be in newtons. We are going to track the normal force on the block. Normal force is in newtons as well. But we can't directly calculate these values. So instead, we are going to measure out values for the mass of the block. And we'll use grams. I'm going to leave a line there. So our experiment will have us take this route. Okay. Well, for our experiment, we have a block here. I take this block, I put it on the scale, I weigh it out. Let's see, we should have all right, we'll round that to 150 grams. So, what I'm going to do up here is I'm going to write mass of the block 150 grams. Sound good? 150 grams. If our block has 150 gram mass to it, we then ask, well, what is the weight going to be? Well, weight is easy, right? To find weight, we just do mass times acceleration due to gravity. So what do? We take 150, we multiply by 9.8, we're done? No, why not? You have to make it into kilograms. We have to first convert to kilograms. So 150 grams is how many kilograms? 0.15. So we take 0.15 grams, 0.15 kilograms. We multiply it by the acceleration due to gravity, 9.8. And what do we get for a weight? .47 newtons. That seem all right? 1.47 newtons. Okay. Then we ask the question, well, under this circumstance, we have our block on our surface. We pull it across. We ask, what is the normal force? Well, here it's easy. Because we look at our block, and if we pull it left and right, is it accelerating up and down at all? No, there's no vertical acceleration, and in the case of our experiment, the vertical acceleration will always be 0. If the vertical acceleration is 0, what does that tell you about the vertical net force? Also 0. So we get this normal force minus weight is equal to 0. or in other words, the normal force is equal to the weight, 1.47 newtons. Now there's a reason why I'm going through this process. But do we feel okay about that? All right, cool. So here's what I'm going to do next. I promise there's a point to this. I'm going to take this 200 gram weight. Take this 200 gram weight, put it on the block, and then I ask, with this 200 gram weight and the block, the scale will read, what, 350, right? The scale will read 350. That's how much mass is on the block. Does that sound good? So we ask ourselves, well, what is the mass of the block? Still 150. Just because I put a mass on the block doesn't mean that the mass of the block changes. So the mass of the block stays at 150. The weight of the block is still 1.47 newtons, but something changes because now when we look at this block on the surface now has to push harder up on the block to support more weight, right? So we ask, how much normal force exists there? How much normal force exists there? Well, building a free body diagram for this new case, we'll have tension pulling on it soon. We'll have it moving, kinetic friction. We're not too worried about the horizontal motion yet. We're only looking vertically. And vertically, we have normal force. Going down, we have the weight. We also have the added mass, adding extra weight to the system. So I'm just going to add a W there to represent the added 200 grams of weight. And when we do this, we'll find that still the vertical forces cancel out. So the normal force must be the weight added plus the weight of the block. And what will this equal? This will equal 350 grams or 0.35 kilograms multiplied by 9.8. And what is our new normal force? Was it? 3.43 newtons. Does that sound good? Feel all right with this? Now I'm doing this to drive home this idea that the weight of the block is not changing, but the normal force is. As we add mass to our object, the normal force is changing. Not the weight of the block, but the normal force. So we'll do one more. I am now going to add 400 grams to our block. I add 400 grams to the block. The block still has a mass of 150 grams. The block still has a normal force, has a weight of 1.47 newtons. But we now have an added 400 grams, bringing our normal force to being 0.55 times 9.8. 0.55 times 9.8 gives you what? Was it? 5.39. 5.39 what? Newtons. Again, as we add mass, we are not changing the weight of the block, we are changing the normal force. By adding mass, we change the normal force. And that is key to this experiment that we are going to undertake. All right, so now let's get to the actual experiments. So we should all have a piece of graph paper, yes? And on that graph paper, you should have axes that are already labeled for you. Is this true? On one of the sides, we're going to graph together. What's up? Extra graph paper in the back. All right, so what is our experiment going to entail? We are going to have a block sliding across the surface. We are going to propel it across the surface with some masses that are going to be hanging off the edge. I'll give you guys a second to settle back in. All right, so in our experiment, what we are going to do, we are going to have a block. Perhaps our block will have some masses on top of it. And what we are going to do is hang some masses over the edge of our block to get it to propel forward. So if you look at the setup I have right now, the block propels forward with a mass that is hanging. Does that sound good? We are going to track two things. We are going to track the mass that is sliding, and we'll keep that in grams. And we are going to track the mass that is hanging, and we are going to do this in a very specific way. Because we are going to look for the cases in which our object is in what we call dynamic equilibrium. We think back to that word equilibrium, but we remember what equilibrium meant. What was equilibrium?
Balanced forces.
Balanced forces, meaning the net force is zero. If the net force is zero, that means what about the acceleration? Not that it's not moving, but the acceleration is zero. Not moving is a case of acceleration zero, but it's not the only case. Because an object can be traveling with a constant velocity. And if it's traveling with a constant velocity, it can still have zero acceleration, can still be in equilibrium. So we are going to look for the case of dynamic equilibrium, that is equilibrium of an object that is dynamic, meaning an equilibrium of an object that is moving. So I'm going to go ahead and start off. Load up this object with a bunch of weights. We're all going to pay very close attention to this, and we're going to see, do we think that this is in equilibrium, or do we think that it's accelerating? Okay, ready? It was accelerating, so it was not in equilibrium, right? So here's what we can do. We can load up some mass onto this object. Now, does adding mass change the weight of the block? No. Now, what does it change? Normal. So we let it go. We say, well, that's not moving, so certainly that's equilibrium, but it's not dynamic equilibrium, right? So what we can do, add a little bit more mass down here. And when we add a little bit more mass, even more than that, we start to get it to move. And what do we think about this? Does that look constant speed? Yeah, just about. We can reset it. We can take a look at this one more time. All right, it's sliding, it's sliding, it's sliding. It looks pretty constant speed. Yeah. We'll call that dynamic equilibrium. So we have something that's in dynamic equilibrium. What does that mean? That means that the tension going to the right must cancel out the force of friction. We were using F subscript K for force of kinetic friction. But the tension to the right, the tension in that string, must cancel out that kinetic friction. Sound good? Well, the tension going to the right, that's going to be dependent on how much mass we are hanging. More hanging mass means more tension. So we keep that in mind. All right, so here's what we're going to do. We're going to start out by So we're going to start off by looking at this thing and saying, okay, well, the block has a mass of 150 grams. I put an extra 400 grams on it. How much mass is on that block? Or how much mass is total? 550, yeah? So we have 550 grams of mass on the block. So we'll use that as one of our data points, 550 grams on the block. And what we're going to do is we're going to take the mass that we have hanging, we're going to place it on the scale. Take all of this mass, I don't want to untie it from the strings. Take all of this mass, put it on the scale, and I'll measure it out. And that'll be, we'll round that to 140 grams. Sound good? So we're graphing this, we're all graphing this together. We take our graphs and we start to put in our data points. And what we have is a sliding mass that is at 550, that's what I wrote, 550 grams. So we go 400, 440, 480, 520. What did I say it was, 550? So that would be what, 560, 560, so we'll say 550 is somewhere around here. And then we go up to 140, right about there. So we put a data point right there to represent the data point we just took. And it should be at 550 and 140 grams. Sound good? All right, now what we're going to do is we are going to increase the amount of mass that is on our sliding block and put an extra 150 grams on. So now we have 150 gram block, and we have 2, 4, 5, 550 grams added to that, giving us a total of 750 grams. So this next one we are looking at will have 700 grams of mass that is sliding. If we have 700 grams of mass that is sliding, do we think that we will need more than 140 grams of hanging weight or less? More, makes sense. Heavier object, harder to move, so what I'm going to do is hook on the original 140. Let's see, we hook on the original 140. It's definitely not moving, so we add some mass to the hanging. Still not moving. Add a little bit more. And let's see. Does that look like it's constant velocity? Yeah, just about, right? Just about. So now we have a data point that's at 700 grams for our sliding mass. And we take this, we put it on our scale. About 175 grams. So we go ahead and we put that data point on there too. So we take a look at our graph and we plot, let's see, so it would be 600, 640, 680, 700 probably be somewhere around there. So we have 700 grams and we have, what did I say, 175? 175 would be 175, so we have our data point right around there. Can we see that? Cannot on the recording. I'm going to slide this down. So we have our two data points on our graph. Does it seem all right? Seem like it makes sense? All right, we'll do one more data point. We'll do one more data point. This time we'll go lighter. This time we'll look at, I don't know, let's say, we go lighter. We have the 150 gram block with an added 50 gram mass. 150 gram block with an added 50 gram mass. What is our total mass that is sliding? 200, absolutely. So we have 200 grams that is sliding. We want to take a look here at how much mass it takes to get it to be in dynamic equilibrium. So we take our mass from earlier, we load it up, try that much, put it on there. We let it go and we say, well, that definitely wasn't dynamic equilibrium, that was speeding up. So let's try a little bit less weight than that. We go through the process of experimentation, remove some weight, see if that'll work for us. That's closer, still looked like it was speeding up a little bit. So I'm going to even remove a little bit more weight than that. And let's see, is this going to give us a nice constant motion? It's nice and slow, doesn't look like it's speeding up out of control, it's not coming to a stop. I'd say that that's probably dynamic equilibrium or thereabouts. So what we're going to do is take this mass, see how much we have on there. Okay, we'll round that to about 50 grams. So we make our last data point. Our last data point of the 3 data points that we're tracking here. And if we were being good about our experimentation, certainly we would take more than that. But 200 grams, we had 50 grams for our data. And what do we start to see on our graph? What are we noticing here about our graph? What was that?
Less sliding mass, less hanging mass.
Less sliding mass, less hanging mass. Absolutely, that is true. Less sliding mass means it takes less mass, hanging mass to get it moving down the row. Absolutely, that's true. But what else do we notice? Do we notice anything about the way the graph looks? It's linear. It seems to be forming a straight line. And you can take more data points, you can find more data points on the graph, but you should see that it does in fact form a straight line. And if you take that straight line, we come down here, put all 3 on there, and if you strike a straight line onto your graph, we can start to analyze this straight line. You analyze this straight line. Well, how do you analyze a line? Well, there's 2 values that are going to be of interest to us. The y-intercept is of interest. And what does the y-intercept end up being here on our graph? 0. Right? If we look at that line, it seems to go through 0, 0. So our y-intercept here, our y-intercept is equal to 0. And we ask ourselves, does that make sense? Does it make sense? Raise your hand if you think it makes sense for 0, 0 to be one of the data points. All right. Here's what I want you to do. I want you to turn to your neighbor and I want you to tell them why you think it makes sense for it to go through 0, 0. All right, who wants to tell the class why it makes sense? Anybody? They're all just talking. Sure, someone has an answer. We can wait. I love awkward silence.
My guess was that it's at equilibrium there, there's no weight, no
Yeah. It makes sense for an equilibrium point to be if there's no mass, then it requires no weight to pull it, right? That's absolutely it. Equilibrium would be reached if the mass that was sliding was zero and if there was zero mass pulling it. That would still be a condition of equilibrium, albeit a very uninteresting equilibrium, because it would be saying nothing about nothing. But it still is a point of equilibrium. That is absolutely true. Now we ask ourselves about the other thing that we use to measure out our behaviors, right? To analyze our behavior. We have y-intercept. What's the other linear thing that we care about? Slope. Absolutely. We care about the slope of the trend line, right? So we want to know about the slope of our trend line. How will we find the slope of our trend line? Well, we look at rise and divide it by run. So we select two of our data points. Perhaps I select this data point right here, and I select this other data point right here. I look at those two data points and I ask, well, what is the rise? The rise is going to be, one more down. The rise is going to be the vertical change between those 2 points. The upper point is 140 grams and the lower point is 50 grams. So that's a change in what? 90 grams, absolutely. So we have a 90 gram rise. We then ask about the run. The run is going to be the distance horizontally moved. When we look at that horizontal movement, well, I've cut off the axes up here, so I don't actually know. Someone that has their graph. 350. 350 what?
Grams.
350 grams. Perfect. So we have a run of 350 grams, a rise of 90 grams. What then is our slope? What is it? 0.257? Sure. 0.257. And the units cancel out. We have grams up top, grams on the bottom. So we have this behavior. What does it tell you? It tells you that the hanging mass is going to, the hanging mass is going to be 0.257 times the sliding mass. And that would give you an equilibrium point. Sure. That's the experimental side, right? We do all of this experimental work. And then the question is, well, how does that relate then to the theoretical work? So we do all of this experimental work. We hold it in our mind while we shift gears and talk about the theory. Because physics is all about the theory. We want to come up with ways to mathematically make predictions. So we go back to this free body diagram business. Actually, let's go back to the interaction diagram, right? We had the block, we had the rope, we had the surface, and we had the entire earth, and then we had the added mass. Yes? Is that everything that we had, though? I would argue something's missing.
The friction.
What was that in the back? The weight on the rope, the hanging mass. The hanging mass, which was crucial to this experiment. If there was no hanging mass, then our object wouldn't have moved. So we have everything that is interacting with everything that we'll actually care about here. Could we include other things? Certainly we can include the foundation of the building, supporting the table, supporting the surface, whatever. But we don't care about all of that. This is all of the things that we are going to care about, and we are going to have interactions between surface and block that is going to be twofold. We have a normal interaction, a normal force, and we have a frictional force. We have a gravitational force, a tension between the rope and a tension between the hanging mass. And we have the entire Earth connecting to that hanging mass through a gravitational interaction. We got all these things. And what we learned from analyzing the block is that the force of kinetic friction is equal to the tension. Right? That's what we learned from the block. Okay. What else did we learn? We learned that the normal force is found by the combination of the weight added plus the weight of the block. We learned those two things from the block, yes? I've already written this out at some point, but do we feel okay with that? Right? We understand where that comes from. Well, I want to rewrite this normal, because the normal force can be rewritten as, well, the weight added and the weight block. That is going to be the mass added times g plus the mass of the block times g as well. Because weight can always be calculated by taking the mass and multiplying it by the acceleration due to gravity. We feel okay about that. We then move on to ask the question, normal force, which can be described by the added mass plus the mass of the block multiplied by acceleration due to gravity. Can we simplify this further? We ask the question, can we simplify this further? And the answer is absolutely, because we were doing this calculation at some point where we were adding mass of the block to whatever we put on top of the block. And we were using that in our experiment. Where did we see that in our experiment? The sum of our masses was the mass that was sliding. The sum of the masses of the mass of the block and the added mass, that was the mass that was sliding. We called that the sliding mass. So we'll say that the normal force is equal to the mass that was sliding times g. Okay, now we're getting to a place where our experiment that we did, that we were unclear why we were doing this experiment that we did, well, now we're getting to a point where some of the measurements that we took are showing up in the theory. But we are still missing something. We're still missing the hanging mass. How does that come into play? Well, if we want to know about the hanging mass, perhaps we shift our gaze to the hanging mass as a system. Because we can look at the hanging mass, and from the hanging mass we can build a second free body diagram. And from that second free body diagram, we can gain even more information. We can create a second free body diagram for our hanging mass, and when we do so, we should have two interactions going on. We should have the interaction between the rope and the hanging mass, because again, that crosses that boundary between environment and system. So we have an interaction between the rope and the hanging mass that crosses that boundary. And what is that interaction? Tension. Remember, ropes, strings, wires, they all cause a tension for the force. And we look at our hanging mass, and when we have our hanging mass, the tension will be pulling vertically upwards, right? Take a look at, well, I don't have any mass on there right now. I'll put the mass on there for an example. We have the mass hanging off to the side. The rope is pulling up on that mass, so the tension must be upwards. So we have the tension going upwards. What is the other interaction that crosses the boundary between environment and system for our hanging mass? Gravity. And gravity goes which way? Downwards. Okay. Now we asked a crucial question here. We asked a crucial question. Can we determine any sort of information based on this tension and gravity? Well, certainly we can apply Newton's second law. Tension minus gravity is mass times acceleration, but can we do better than that? And I want to take a look at this block and this mass. If I slide the block to the right, the mass, sorry, not right and left. If I slide the block to the left, the mass rises upwards. If I slide it to the right, the mass lowers. And if I do it quickly, the mass raises up quickly. If I move it to the left slowly, the mass lowers slowly. What's interesting here is it seems as though they share a speed. The block and the hanging mass share a speed. And if they share a speed, then they must share a change in speed, right? So if they share a change in speed, what does that mean about the acceleration? They share acceleration. But we know something about the block's acceleration. We've done the experiment so that the object was in dynamic equilibrium. Equilibrium meant the acceleration of the block was what?
0.
So that means the acceleration of the mass that is falling is 0 as well. When two objects are connected to each other, whenever you have two objects that are connected to each other, they're going to share motional quantities. They're going to share velocities, they're going to share displacements, they're going to share accelerations. So our mass and our block, which are tied to each other, would share accelerations, telling us that tension minus that gravitational interaction, I should probably be putting W here, not to confuse us with the acceleration due to gravity. This is the gravitational interaction, the weight. So what this tells us is that the tension minus the weight is 0, or in other words, the tension is equal to the weight of our hanging mass. And the weight of the hanging mass is found by taking the mass that is hanging, and multiplying it by g, 9.8. And this is where we get the connection between the two variables that we were taking a look at, the hanging mass and the sliding mass. We get that connection because we now have our tension linking the hanging mass to the sliding mass. The tension links the two. And since the tension links the two, we suddenly get to a point where we can say the force of kinetic friction, which is equal to the tension, well, that means the force of kinetic friction is going to be mass that is hanging multiplied by acceleration due to gravity. Does this seem okay? All right. Wonderful. Now, we discovered something. We discovered something, though, with our graph. We discovered that there's a linear relationship. There's a linear relationship between the sliding mass and the hanging mass, right? And what we found was that the mass that is, what did we have on the vertical axis? We have the hanging mass on the vertical axis. All right. So we have the mass that is hanging is equal to 0.257 times the mass that is sliding. Yeah? Again, I promise you this is going someplace. because taking mass that is hanging and mass that is sliding and plugging in for the two theory parts that we found, well, that would give us mass of hanging is equal to the kinetic friction force divided by g, right? Mass that is hanging is kinetic friction over g. I think I got that right. So we can then replace mass that is hanging with kinetic friction divided by g, and that's 0.25 multiplied by the mass that is sliding. But the mass that is sliding can be rewritten as normal force over acceleration due to gravity. We see that where that came from, yes? Hopefully? Yeah? Because this gets us to a very important relationship. G is on both sides of the equality. So that cancels out. We end up with force of kinetic friction is 0.275 times the normal force. We get a relationship that specifically tells us about the relationship between the kinetic friction and the normal force. And maybe this should make sense, because if we remember our interaction diagram, the friction force and the normal force were between the same pairs of objects. They're both between the surface. They're both between the surface and the object that is moving, the sliding block in this case. So perhaps they should be linked. And they absolutely are. We have that the kinetic friction is related to constant times the normal force. We can be a little bit more general about this. We can be a little bit more general. We can take this kinetic friction and we can say that the force of kinetic friction between any two objects, again, I could have chosen anything. I chose this wood block. But let's imagine I chose an object that had a very, very rough surface, right? If I had a rough surface and I put it on there, it would take more weight to move because the rough surface would give it more grip. So the slope depends specifically on what objects we are looking at. In this case, we got 0.257. If we switch out the object and the surface, we would get some other value. So what we can do is say that that slope has some constant value depending on what materials are present. And we use the Greek letter mu to represent this constant. Mu with the subscript k says that this is the friction constant for kinetic friction. Not static friction, but kinetic friction, multiplied by the normal force. And this is the equation that will always calculate for you the kinetic friction acting on an object. So earlier when we were talking about gravitational force, well, we have an equation for that. Normal force, we don't have an equation for that. Not an always equation, right? Normal force depends on the scenario. Friction is a force that gives us, or kinetic friction, is a force that has an equation that will always give you the value. And it's by taking a constant and multiplying it by the normal force. And this constant, the friction constant, is the coefficient of, in this case, kinetic friction. There's a similar one for static friction. We have this coefficient of kinetic friction, which depends on what materials are present. In other words, how grippy is the surface? How much grip is between the surface and the object that is trying to slide on that surface? So we have now this way to identify the force of friction acting on an object. And we can implement it. We can implement it to ask questions such as, So you can start to answer questions that ask how much friction is acting on some object that is sliding on some surface. When you're asking this question, it is important to understand that what type of surface and what type of object is important. Because the combination of surface and object give you that coefficient of friction. In this case, the kinetic friction coefficient from the analysis of what objects are present is given by, well, we just measured it, 0.257. So we would say 0.257. All right, then you ask, okay, well, what is the block's mass going to need to be? So we give a mass of the block, so we'll say a 2 kilogram wood block. So we say here's the mass of the block equals 2 kg. And now with that understanding of what block is present and what surface and block materials are, you can find a value for that coefficient of kinetic friction. All right, very theory-heavy day, but I hope you guys feel satisfied with the fact that I didn't just give you this equation, we proved it. We proved beyond a shadow of a doubt that this is the relationship for kinetic friction. We build this equation from an experiment, so from physical reality, and from all of this other material that we've been building on all semester. So we've come to this understanding of finding this equation that does in fact fit reality. All right, next time we are going to talk a little bit more about another type of force. We're going to talk about spring forces, and then we're going to do a little bit of problem solving. But before you go, let's see if I can do this. Before you go, I have a new card for you. This new card gives you descriptions of a few different forces in which we have equations for. And this includes now the kinetic friction equation we just came up with. If you don't mind passing it. Okay. We don't have much time left. Remember, before you leave, we have your test reflections that you need to turn in today. I want to see those today. You have, if you did a makeup lab this week, be sure to turn that in as soon as you can. And I think that's all for important announcements. We have homework 5. Homework 5 is coming up due. You should be able to solve all the problems on it. It does involve some amount of graphing, yes.
For the corrections, do you want us to staple this cover page, or do you also want us to staple our test?
You do not need to staple the cover page or the test. I just need the reflections that you did. If you did staple the cover sheet, that's totally fine. If you stapled the test, you might want to hold on to the test, but I'll take whatever you give me. Any other questions? All right. If you guys stay behind, I have some exercises that we can work on in office hours. Otherwise, have a wonderful weekend. Enjoy your 5 or so minutes heading out early.